Today we're going to look at equation solving using logarithms. And in the process, we're also going to discover a very important formula that will help us with many other types of logarithmic problems. Let me start off with an example and show you how useful logarithms can be. Here we have 2 to the x equals 5, and we want to try and solve for x. Well, what I'm going to start off and do is take logarithms of both sides. Okay, and I'm just going to work with common logarithms, or base 10. Now, why would I do that, you might think? Well, the reason is I can now bring the x out in front, and it's no longer an exponent. So I now have x times log 2 equals log 5. To solve for x, I simply have to divide both sides by this number. Remember, log 2 is just a number. This can be done on a calculator quite easily, and the answer is approximately 2.3. So that's how logarithms can solve what at first might seem like a very difficult problem, but it's not difficult at all once we decide we're going to use logarithms. Let me show you a more complicated example. Okay, in this example, I have 3 to the x plus 2 equals 5 to the 2x minus 3. So a little bit more involved exponents. But once again, what do? I take logarithms of both sides. And in doing so, I can now bring these exponents out in front. Now here's where you have to be careful. All of this is the exponent, so I bring all of that out in front with brackets. Now what you actually have here is x plus 2 times this number, log 3. Same sort of thing happening here. I'm going to have 2x minus 3 times this number, log 5. Now you can proceed in many different ways, but what I recommend you do is expand out the brackets, so that what we now have is x times log 3 plus 2 times log 3. And the same sort of thing over here. I'm going to have 2x times log 5. So 2x times log 5. And then minus 3 times log 5. The trick now is to bring all terms that have an x in them to one side, and everything that doesn't have an x in it to the other side. So a little bit of rearranging here. So I'm going to have x times log 3. Then I'm going to subtract this 2x times log 5 over to the left. So minus 2x log 5. And that's going to equal this brought to the other side. So negative 2 log 3. And then we have minus 3 log 5. So now we use a very neat little trick. Both of these terms have an x, so we factor that x out. So that gives us x on the outside, log 3 minus 2 times log 5. And on the right side, all of this stuff just as before, minus 3 log 5. And lastly, to solve for x, I divide both sides by this stuff here. So here's what we end up doing. we're going to take all of this stuff here, minus 2 log 3, minus 3 log 5, and divide that by log 3 minus 2 log 5. Now when you do this on the calculator, the easiest thing to do is just put a bracket, type all this stuff in, close the bracket, divide, bracket, put all this stuff in, and close the bracket. You've got to be careful that you're dividing by all of that stuff. It's very easy to miss a bracket here or there. When this is done, we can get an approximate answer for x, and that answer is about 3.3. So a little bit more involved algebra, but very doable. Okay, now let me do another example. And this next example is going to illustrate a very important formula. So, I'll need lots of board space. Okay, so this next example looks like this. I'm going to try to figure out log and use a different base. Base 5 of 782. Now normally you can't do this on your calculator. So how do we solve this mystery item? How do we tackle this? Well, I put this in exponential form, which would be 5 to the unknown, and that has to equal 782. And now I'm going to take logarithms of both sides and try to solve for the unknown. So logs of both sides equals log of 782. And I'm choosing base 10, although it doesn't have to be base 10, but that's a good one since that's on our calculators. We can bring the exponent out front. And solve for the unknown now by dividing both sides by log 5. And we do come up with an answer. It's approximately 4.14. Now this little example will demonstrate a certain formula for us. You'll notice what happened here. In order to solve log of 782 base 5, what we ended up doing was log 782 divided by log 5. We chose base 10 because base 10 is on our calculators. But as I mentioned during the example, it could have been any base that we wanted. This is called the change of base formula. And let me just write that out now in a more generalized form. Okay. So what we have would look like this. If we have log of, we'll say, A base B, if we want to try and unravel this, we can directly go to log of A over log of B, and you can choose any base you want. Now, commonly that would be using base 10, common logarithm, but I'm just going to write down base C because technically we can choose any other base. And sometimes there is a reason that we like to choose a certain other base. Let me show you another spin-off of this formula, which is has to do with exactly that particular special choice of base. So suppose we started off with this, and we go to log A over log B, but this time I choose base A. Now, why would I choose base A? Well, the numerator, log of A to base A, now you think about this, A to what exponent gives you A? 1. So that's kind of neat. And so on the bottom we still have log of B to base A. So you can see it's a kind of a flip-flop action. We have log A base B, and that equals 1 over log B base A. That being said, the most common use of this particular formula is to unravel situations where you have a base that we don't have on the calculator, and I change it to something that I can handle very nicely. And a quick example of this would be, suppose you wanted to graph something like this, and you're going to do this on your calculator. You wanted to see, well, what is the graph of y equals log base 3x? You know, if I wanted that function on my calculator, how could I do it? Because there's no log base 3 button. However, what you would do is say, well, the change of base formula allows me to do this. I could use log of x and use base 10 divided by log of 3 base 10. And that's just using this change of base formula, and now I've got a version of the same function that my calculator can handle, that it can understand, and produce a graph. So very, very handy little formula. Let me show you another little trick with this formula. Sometimes we use it to do what are called proving trigonometric, or sorry, logarithmic identities. Getting my mathematical concepts confused. All right, logarithmic identities. We're going to try and prove something like this. 1 over log of 8 base 5 plus 1 over log of 8 base 6. We want to try and prove that that equals 1 over log of 8 base 30. Now that's a pretty bizarre looking identity or statement. In order to try and prove this, I'm going to use totally the change of base formula backwards. Now, in other words, what I'm going to do is this. Just look at this first one here. 1 over log of 8 base 5 would be the same thing as log 5 to the base 8. We just kind of flip-flop. Plus, you're probably starting to see how easy this becomes. We flip-flop these two, and we don't have to write it as 1 over, so it becomes log of 6 base 8. We're trying to prove that that equals this. When I flip-flop these two, well, all of a sudden it doesn't look so tough anymore. I look at these two things, they have the same base, so I can combine them, their addition, so these would be combined through multiplication. And you can see clearly this is going to be the same thing as log 30 base 8. Pretty simple question once we use this change of base formula in action. And then my last example, I'm going to solve a logarithmic equation. Not that I haven't been doing that the whole time, but this is one that's kind of a little bit more interesting, I guess. What we have is this. We're going to try and solve the following. Log base 5 of x minus 6 equals 1 minus log base 5 x minus 2. And we're going to try and find x. So how do we do it? Well, I think the easiest thing to do, and there are different versions, different approaches, but I'm going to bring this logarithm, this stuff here, and add that over to the other side. So I'm going to have log base 5 of x minus 6 plus log base 5 of x minus 2 equals 1. So I've simply added that over to the left side. These are both base 5, so according to the laws of logarithms, when we're adding, that's the same as multiplication. So I would have this. Okay, well, we've kind of gone as far as we can with logarithmic stuff. Now I'm going to change to its exponential counterpart, which would be 5 to the 1, equals all this stuff here. Now this stuff here I'm going to write, but my next step would be to expand all that out. So I have 5 to the 1 is 5, equals x squared, and then I have minus 2x minus 6x plus 12. Well, this looks like a quadratic equation. So I'm going to try and get everything on one side, combine some like terms here, so minus 8x, and I've taken 5 away, so I have just plus 7 remaining. Now, to solve a quadratic equation, you can use a quadratic formula. You can use completing the squares, although that's probably more work than it's worth. Or you can use a very good method, which is factoring. I think this looks like it might factor, so that's what I'm going to use. X and an X, and to get positive 7, but have the factors add up to negative 8, I'm going to use negative 1 times negative 7. So negative 1 times negative 7, adding up to negative 8, but multiplying together to make positive 7. And so my solutions would seem to be x can be 1 or x could be 7. Now here's the really, really important part of these logarithmic equations. When you think you're done, you have to take your answers and try them out in the original equation. Because what you might find happening, for example, if I use the number 1, is I'm trying to take the log of 1 minus 6. Well, that's a negative number. And if you recall, the domain of logarithms has to be greater than 0. So 1 doesn't work. It fails here, and it also fails here. It just isn't working. So you reject that guy. As far as the 7, however, that's good, and that's good. So we consider the 7 a viable solution. And that's how we solve logarithmic equations. Some get a little bit more miserable. Some are easier. This one's kind of in the middle. Lots of fun. Okay, I think we're going to stop there. So